So in our previous video, we discussed what a knowledge graph is. We spoke about the key components of a knowledge graph. First, we said that it's composed of nodes and then also relationships between the nodes. In the context of education, a knowledge graph is just a set of knowledge components that has prerequisite or post-requisite relationships amongst them in the context of this presentation. There are many techniques that are used to learn them. And so for today, or in this module, we're going to be talking about the techniques for creating them, some of which are, machine learned, and a few other statistical approaches. We will also then talk about, application of knowledge graphs in the context of education. Now, building or creating a knowledge graph. Well, there are three main areas. First, they are expert-made. The majority are expert-made. And then you have another set that is actually also learned from existing student performance data. And another set of approaches which combines the two. So an expert comes up with a design, we collect data around the expert created knowledge graph, then we go back and refine it based on the performance data we get. Let's start out with the expert designed graphs. So typically, if you're an expert in your area, it's understood that you know what any new person coming into the domain needs to learn to be able to get to your level, right? So you know what the key knowledge components are, and you can identify them, and you can tell what the order is for this new person or that's learning, wanting to be like you would be able to do. So generally, it's like that. So if, let's say, we want to create a set of or a knowledge graph for a domain like elementary school math, we can look for really good elementary school math instructors. We can get mathematicians who understand the key concepts of these key knowledge components. They can then identify them. These aspects can then decide, okay, now which one should a student learn before the other? We think this is better than that, and they can put it together, and that becomes a knowledge graph. In the assessment system, especially when they created a system they called placements, they used such a knowledge graph, which was expert designed. All right. Now, it's not only in learning management systems where you find knowledge graphs of that nature. In typical textbooks, you'll notice that an author would come up with his own set of, topics or chapters in a textbook. The chapters they can be looked at as, a very high level knowledge component. But usually the authors are likely to give you in the preface or somewhere like that, the order in which they think you should learn or teach students this material. That is itself an expert-made knowledge graph, right? Suggestions as to how to study the material, and sometimes they even include, different paths for different people that are reading the material. These can be reviewed by others. It's an expert-designed knowledge graph, right? Sometimes, though, these knowledge graphs are learned from data without any prior information about knowledge components. And we'll talk about one such technique shortly. There are others that just go through textual data. And there's an example I read about in which the author basically took the course descriptions for each of the courses in a particular program. He tried to build a prerequisite relationships amongst the courses just on the basis of the course descriptions. That is from data. The data is textual and it works. So we're going to talk about one of those techniques. And the technique I'm going to talk about is the learning of a Q matrix or Q matrices from student performance data. Now, what's a Q matrix? You may ask. Well, I'm sure you hear and you can see the word matrix in there. So clearly, it's making reference to a structure, a data structure that is made up of rows and columns. The rows represent items or questions, and the columns represent the skills or knowledge components that are associated with the skill or with the item or the question. This was initially proposed by Tatioka in 1983, and then of course Barnes also worked with it and worked on and came up with a technique for learning these Q matrices from data. It has other names. Sometimes it's referred to as knowledge component model, sometimes it's referred to as a skill item mapping, and a few more. In the next slide, I show you a typical example of the structure of a knowledge component. So you can tell from this structure that there's 4 skills here, and there are about 6 items. If we were to take item 4, basically what we're saying is for a student to succeed in item 4, they need to know no other skill or other than skill 4. Now, for a student to be able to answer item number 3 correctly, they should know skill 1 as well as skill 3, and on and on. For example, item number 5 requires mastery of skill 3 and skill 4 to be able to completely and successfully answer item number 5. Here's a typical instantiation of that Q matrix. So in this case, I have 4 skills: ability to add, ability to subtract, ability to multiply and divide. And each of the questions shows you which of the skills is required to be able to successfully answer that question. So for the very first one, for a student to correctly answer that question, they need to know addition. For the very last one, they need to know subtraction and subtraction alone. For the last but one, they need multiplication and division, like that. So this is a very typical example of a Q matrix. But then the question is, how do you learn this Q matrix from student performance data? Barnes et al. Suggested a hill climbing approach, which I'll talk about in the next set of slides. But that's not the only one. Desmarais also came up with a non-negative matrix factorization approach, and Piconis, I hope I'm pronouncing the name correctly, actually combines these two, to be able to identify or learn Q matrices from data. Now let's discuss Barnes et al.'s approach. In Barnes et al.'s approach, the key question is, how many skills do we even start with? Because all you have is a list of students or questions and student responses when they were asked those questions, and whether they got the answers right or wrong. The algorithm is very simple. So you start out by assuming that all the questions belong to one skill. And then you add one more skill to the currently identified set of skills. So, and then you try to figure out whether this new model predicts the student's performance data much better than another one. Better is very subjective, but we can talk about it and how that can be determined shortly. Once you figure out a model that doesn't meet the criteria you want, you could go to step 2, add another skill to it, keep doing that until you get the best model, and then you quit. Now, the best model can be determined in many different ways. How? Well, usually we say that a model is better if, by assumption, we say a student knows skill A, or in this case, skill X, and items 1 and 2 both require skill X to succeed, then the following should be true. 1. If a student gets item 1 right, then they should get item 2 right because they both are tagged with the same skill. If a student gets item 1 wrong, it's implied that they also get item 2 wrong. If they get item 2 right, they should get item 1 right, and then, on and on. If they get item 2 wrong, they should get item 1 wrong. This is the basis upon which we determine whether a model is better or not. So with this understanding, we move on to the next step where we say, let's say you're giving an initial set of skill to item mapping. We'll try and predict whether a student is going to get the items that have been mapped to the skills we have identified for each combination of skills, whether the student gets the item right or not. So the goodness of fit, in other words, the model's ability to predict how well the student answers the question becomes the basis upon which we determine whether a model is good or not. So we keep going through that process until eventually we get to a situation where we're getting a really, 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 really good model. There are many different, metrics that could be used. BIC could be used, AIC, or you could even just do simple cross-validation, just like it's done in Effenberger et al. 2020. There are other approaches for determining really, really good models. Okay. Sometimes you may choose to observe a student's improvement over time. You could also choose to fit models like performance factors, analysis to which I've linked a video in this module. There's also Bayesian knowledge tracing that will be discussed later on. And depending on how the skill to item mapping fits the data, we can determine whether the Q-matrix or skill item mapping is good or not, right? Now, you may ask yourself, okay, so now I'm just learning the relationships between items and skills, but how about learning the structure or the relationship between skills and skills? It's very basic. Just like you have a Q-matrix of items and skills, you could also specify and learn a relationship or infer the relationship between the knowledge components using the same approach as has been done in the past.